Hi guys, today's topic is the kinetic molecular theory and Avogadro's law. Avogadro was one of those really important scientists who discovered a whole bunch of things, and way back in the day, one of the things that he looked at was the behavior of gases. Now, in order to discuss this, it's important for us to know that what he was doing here was he was comparing gases under the same conditions. And by same conditions, I mean the same conditions of temperature and pressure. And so what has been established over the years is this idea of STP, or standard temperature and pressure. So when scientists go and they start to say a gas does this or a gas does that, typically they have to describe the conditions under which the gas is operating, and so consequently they have developed this standard idea for temperature and pressure. Now, what is standard temperature and pressure? Well, for pressure, it's easy. It's the easiest number you can think of in atmospheres, 1. Now, in millimeters of mercury, obviously that's 760. In kilopascals, it's 101.3. There's all sorts of different units that you could use, but those are probably the most common ones that are there. So if you're talking about standard pressure, you're talking about any one of those. Pick one, whichever is convenient for you. All right. Now, for temperature, though, it is 0 degrees Celsius, which is 273 Kelvin. Right? So if you're talking about temperature, you're talking about 273 in the Kelvin zone that's there. All right, so what Avogadro did was he started to investigate a bunch of different gases. And what he found was kind of amazing to him, and it didn't make a whole lot of sense at the time. For example, if he took a mole of helium, so 4 grams of helium at 1 atmosphere and 273 Kelvin. All right, so 4 grams, 1 mole of helium. It turns out that made a balloon that was the size of 22.4 liters. Now, why 22.4? I have no idea. It doesn't matter. But it turns out that's what it was. It made a balloon size of 22.4 liters. So he went, okay, fine, great. Then he went and did another experiment and did the same exact thing with oxygen. Got a mole of oxygen and put it at 1 atmosphere and 273 Kelvin. So 32 grams of O2. And lo and behold, it turned out that it was also 22.4 liters. Huh. And then he did it a third time. He did it with nitrogen, which has another different mass. 28 as compared to 32 as compared to 4. Under the same conditions, 273 Kelvin and 1 atmosphere there, sure enough, it reached 22.4 liters. And this kind of blew his mind a little bit, because he's like, wait, these are different gases. These are completely different gases. Yet, if I take a mole of them, then I'm getting the same result for these guys, 22.4 liters. And so he came up with this law. And Avogadro's law says that equal volumes of all gases at the same temperature and pressure are going to contain the same number of molecules, or moles. So if you've got a balloon that's of a certain size, and that balloon is of the same size as a different balloon, and they're under the same conditions of temperature and pressure, then the moles are the same. So again, the moles here are the same as the moles here are the same as the moles here. So equal volumes of all gases at the same conditions of temperature and pressure contain the same number of moles. Now, as far as the why and the how of everything that's going on, this is a little bit goofy here, because if you think about it, where does the volume of this balloon come from? Well, the volume of a balloon comes from the fact that we've got a particle that is hitting that guy and bouncing off and giving it some kinetic energy. So these balloon particles, or these gas particles, are hitting the balloon, I should say, and hitting each other, and eventually, again, causing a force or a transfer of energy in there so that the balloon goes to a particular size. So Avogadro and all of his science pals figured that this has to do something with the kinetic energy of the moving particles that are in that balloon. Something's got to be going on with the kinetic energy of this. And ultimately what they came up with was called the Kinetic Molecular Theory of gases. And there are 4 basic ideas of the Kinetic Molecular Theory of gases. The first one is not really very controversial. Gas particles are always moving in a random and rapid direction. Okay, so they move around, they collide each other, bing, bang, boom, right? That's number one. Number two, the gas particles occupy a very small portion of the overall volume. For example, this is your overall volume in this picture, this whole box here. But you'll notice that the gas particles themselves, these guys here, if you were to simply smush them all together and add them all up, you might get, what do we got here? 4, 8, 12. You get about 12 dots that are about maybe this size. So maybe about this size. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If I were to smush them all together, they would occupy a very small portion of the actual container. Most of this container here is empty space, which is the whole idea of how gases work. So again, that's not tremendously controversial, although it is going to get us into trouble in some circumstances. But gases are made of very small particles that are very spread apart. That's the basic idea here. Number three is that gases have no attractive or repulsive forces. So in other words, there are no IMFs, right, for these gases. We are assuming they are elastic collisions. There is no energy transfer when they hit each other or the side of the container. No energy is lost, I guess I should say. There are no intermolecular forces. And then finally, this one here is the one that we're going to be focusing on in this discussion. Gases with a higher temperature have more kinetic energy, and gases with a lower temperature have less kinetic energy. The higher the kinetic energy, the faster the particles move. So this guy here says that the kinetic energy is directly proportional to the temperature. So as you get a substance hotter and hotter and hotter, it's going to have more and more and more kinetic energy. But think about that. What does that then imply about these three things over here? If they are all under the same conditions, so whatever temperature these guys are at, if they're all at the same temperature, that means they all have the same kinetic energy. So these guys here have to have the same kinetic energy if the kinetic energy is proportional to the temperature. So as the temperature goes up, the kinetic energy goes up. And if we're comparing different samples here and they're all at the same temperature, all the same, then they all have to have the same kinetic energy, which seems to defy a little bit of logic when you think about it, because here's a mole of hydrogen, and a mole of hydrogen has 2 grams. Here's a mole of oxygen, that has 32 grams, and here's a mole of carbon dioxide, that has 44 grams. Why does that matter? Because we know that the kinetic energy is equal to 1/2 mv squared. So in each of those cases, the mass is going up. So we're going up from 2 to 32 to 44. So if the mass is going up, the kinetic energy also has to go up, right? Well, it can't. The kinetic energy has to be the same. So what does that mean then? Well, that means that if the mass is going up, but these two things have to stay equal, that means in order to compensate for the mass going up and the kinetic energy have to be the same, the velocity has to have a commensurate decrease in the speed of the particles. So if you've got a big mass, you're going to have a small velocity. If you have a small mass, then you're going to have a high velocity, because our evidence quite clearly shows that the kinetic energy has to be the same. So this guy here has a small mass, which means that it has to have a high velocity, whereas this guy over here has a high mass, so he has to have a lower velocity. So basically, as the mass of a gas increases, its speed decreases. So all of that can logically come from Avogadro's experiment back in the day, noticing that a mole of any gas occupied 22.4 liters. And all of this comes from the idea here that the kinetic energy of a sample has to be the same if you are under the same conditions of temperature. Now, what are you going to see about this as far as questions are concerned? There's about 3 or 4 different things that they're going to try to trick you with. The first of which is a simple idea of what we just talked about before, but they might use particulate drawings like this. So for example, this looks like a whole lot of weird arrows and particles and so forth, but check it out. You've got light gases here like a hydrogen or a helium. These guys here are going to have longer arrows. These guys are going to have longer arrows here than a heavy gas like carbon dioxide here. Carbon dioxide is going to have lower arrows, and again, the longer the arrow in these pictures, it's going to describe how fast the particle is moving. So you'll notice that the light particles in each of these cases have longer arrows as compared to the larger particles, which have shorter arrows. Now compare that over here to this picture. The same thing is true. The bigger ones are going to have short arrows, whereas the longer ones are going to come from the tiny particles here. So the ones that are small particles are going to move fast. The ones that are big particles are going to move slow. And then if you compare our two pictures, you can see that our two pictures are at different temperatures, 150 versus 300. And in each case, the 300s are longer than the 150s over here. So the purple 300s are longer than the purple 150s because you're at a higher temperature over here in the 300s. The orange 300s are longer than the orange 150s because you are comparing the same substance at a higher temperature, and the higher temperature it's going to move faster. Now, if you want to actually figure out the speed of the gas, you can use this equation here, but that's not on the AP test, so I don't care about that guy right there. You're not going to come up with him. They're going to have pictures like this. The next thing that they might show you is a graph like this, where you are comparing molecular speeds. This is assuming you are at the same temperature. Now, if you are at the same temperature, then what you're going to get is you're going to get the heavier ones that are going to move faster. So, the heavier ones are going to move slower, the lighter ones are going to move faster. Let's examine a couple of these. Here's hydrogen. It has a mass of 2. Please note that down here you've got molecular speed. So this here is low molecular speed, this here is high molecular speed. Please note that hydrogen, with its very small mass of 2, has high molecular speed up here, or in other words, it's got a very wide distribution of molecular speeds because some of them are going to be low and some of them are going to be high. There's your average molecular speed for the hydrogen that is there. Now compare that, if you would, to something like oxygen. Here is your oxygen that has a mass of 32, much heavier. So because oxygen is much heavier, you're still going to have some down here in the low, but the fast for oxygen, which is here, is not nearly going to be as fast as the hydrogen was over here because oxygen is so much heavier. And so consequently, oxygen, which has that curve, is going to have an average molecular speed of here. So here's the average molecular speed for oxygen. It's way down there. Here is the average molecular speed for hydrogen. It's way up here. And you can see that hydrogen has a much wider distribution of molecular speeds because it has so many more different speeds that it can attain. Because oxygen is slower and heavier, there are fewer molecular speeds that it can obtain, and so consequently, you're going to have more of them at each individual speed because you can reach fewer speeds. So this here is called a Boltzmann distribution graph, and you will see these guys here. This is again comparing different molecules at the same conditions. So again, this is at the same temperature, right? And pressure and everything else being the same. Everything is the same here, and the only thing that you are comparing here is the masses. And so again, you're talking 32, 28, 18, 4, and 2. You can see that the lighter ones are spread out, whereas the heavier ones are taller and more clumped in. Now, that would be a graph that is comparing like this picture here. Everything is at the same temperature, and you are comparing the speeds. What what if you are comparing different temperatures? What if you're comparing purple to purple here? Well, if that's the case, then you're going to see a graph that looks like this. Now, in this case, all of these guys are nitrogen, so mass is not a factor here. But what do you notice? This guy here is cold, and so the cold ones are going to move slower, and so if it's a cold one that's moving slower, you are going to have fewer distributions, so that's slower, right? You're going to have fewer distributions, and you're going to have more of them at each individual speed, which is why your average is here. Now, if you heat the bejesus out of this guy, now you're going to see a wider distribution of molecular speeds, and so you're going to see a higher average speed here for a higher temperature. So as the temperature goes up, you're going to see a wider distribution of molecular speeds. And a wider distribution of molecular speeds is going to result in fewer of them being at each individual speed, which is why it is a shorter but wider graph. If you are looking at something that is cold, again, something that is cold here, you are going to have a small distribution of molecular speeds, which is why you're going to have more of them at each individual speed, and you're going to have a taller graph. So cold graphs are tall and skinny. Hot graphs are short and wide. All right, last thing, they might ask you to compare two different gases in a real-world kind of a setting. Here is an example of two different gases. You've got ammonia and you've got hydrogen chloride gas here that are going to meet and form this ammonium chloride solid that is there. So if the ammonia is put in here and the hydrogen chloride is put in here and they're put in at the same time, please note that they don't meet in the middle. So if you put the red and the blue here in at the same time, they don't meet in the middle. Why? Well, check out their masses. Ammonia has a mass of 17. Hydrogen chloride has a mass of about 36.5. So a 17 is much smaller of a molecule, and so because it's smaller, it's going to be faster. So this guy here is smaller and faster than a 36.5, which is this guy. He is bigger and slower. And so consequently, when these guys are both put in, they meet somewhere closer to the blue 36.5 because it is a slower molecule. Same idea here. If you put in nitrogen and hydrogen into a porous barrier, and these particles are allowed to diffuse or effuse through that barrier, right? Effuse. Diffuse is through air, effuse is through a semi-permeable membrane. Hydrogen has a mass of 2, nitrogen has a mass of 28. So nitrogen is going to be big and slow, whereas hydrogen is going to be small and fast. And so, which one of those is going to get through the barrier easier and faster? Well, it's clear that the little guy over here is going to be easier to get through. He is smaller and faster, so more of them effused faster than the larger one here because the larger one is big and slow. So the smaller particles effused faster through this because they were easier to get through the barrier, whereas the larger one didn't do it as fast. So that is the kinetic molecular theory of gases.